Welcome to qnawire.
So we're given three wires arranged in an equilateral triangle like this, with each side being 3.5 centimeters. And we want to find what the net magnetic field will be midway between wires M and N, so at what I've labeled point O here. So to start, let's just find the magnitude of magnetic field that each of these wires produces at this point, and then we can worry about what the directions will be and break them into components and recombine them to find the total magnitude and direction of the field. So wires M and N, they all carry the same current, 8 amps. So wires M and N are the same distance away from point O, so they must produce the same magnetic field then at that point. So we can say the magnetic field from N is just going to equal that of N, at least the magnitudes. We haven't really thought about direction yet. So those have to be equal, and the magnetic field from a wire is just mu naught over 2 pi times I, and then over the distance to that point. So the distance from point M or from point N, the same thing here. So that distance is just half the side of a triangle, so 1.75 centimeters it looks like. So we'd have mu naught times 8 amps over 2 pi, and then 0.0175 meters. And that should come out to be 9.143 times 10 to the minus 5 Teslas. So now for point P, we have the same current, we'll have a different distance. So our distance is now going to be this, but this is a right angle. So if this is an equilateral triangle, that means this angle here is 60. And so if we're bisecting this one, this is 30. So we can do this a bunch of ways now. So if this full side here is 3.5 centimeters, then this side over here, we can do a cosine of 30, and we would get √3 over 2. So RP equals √3 over 2 times the length of a side, so times 0.035 meters. So we can say the magnetic field from point P then is mu naught over 2 pi times our current of 8 amps, and then over √3 over 2 times 0.035. This is still just the magnitude. And that should come to be 5.279 times 10 to the minus 5 Teslas. So now we want to look at the directions here. So just using the right-hand rule on wires M and N, so we point our thumb along the direction the wire is going and then curl our fingers around. So we can see they're both going to actually be pointing in the same spot. So M will be making field lines like this. And so they'll be going this way. And so they're going to be making a right angle at this point. And then N will be doing the exact same thing. So it'll be looking like that. So we'll have two lines. So for BM and BM pointing like this. So both making 90-degree angles with this side of the triangle. And then for point P, so this is BM and BN. And then for point P, again, by the right-hand rule, we can see it's going to be making lines like this, and they should be going this way. And so out here, it's actually going to be parallel with this side of the triangle. So it'll be making a line like that. Well, a little bit more circular, but something like that. So it will be pointing out along that direction. So now we need to break these into components. So we know that BP is making a 60-degree angle with the horizontal, since it's making a similar triangle here to the overall triangle. And then the other two, BM and BN, then have to be making 30 degrees below this line, since that's a right angle. So give ourselves a little more space to work with here. But we can say then the x component of this is going to be, well, we'll say 2 because we have 2 identical fields for Bm and Bn. So 2 times this magnitude, and then we'd want to do, it looks like the cosine of 30 degrees. So we'll have 2 times, I'll just call this Bm, and then cosine of 30. And then from field P, this will also be positive, and this will be the magnitude of BP, and then times cosine of 60. So plus BP cos of 60. And so this should come to be 1.849 times 10 to the minus 4 Teslas. And now for the y direction, I'm doing pretty much the same thing. So we have 2 times, we'll say the magnitude of Bm again, but Bm equals Bn. And it looks like this is going to be in the downward y direction here. So I'll just say a minus, and then we'd want to do sine of 30. So negative 2 Bm sine of 30. And then BP looked like it was going to be in the upward direction, so plus BP, and that'll be a sine of 60. And so when we do that, we should get negative 4.571 times 10 to the minus 5th Teslas. So for the net field then, we're just combining, we combined all the individual fields, and now we're looking at their components. So we can say our angle should just be inverse tangent of, we'll want to do by over bx. So our net field is looking something like this. We have this x component, and then we have this y component. So in that direction, so we have this angle theta. And so we do that, and we should get 14 degrees for theta, so negative 14 degrees from the x-axis. And our magnitude, we just say that B net equals, just add these in the square root, so bx squared plus by squared. And that comes out to be 4.93 times 10 to the minus 4 Teslas. So there we go, our magnitude and our direction at point O.